G'day viewers. In this segment we'll talk about framing messages which are sent across the link layer. So the need for framing arises because the physical layer delivers a stream of bits. We've worked hard with modulation to turn signals into a stream of bits, but of course a stream of bits is not really what we want. We would like to be able to send a sequence of messages called frames across the link layer, so we need some way to delimit the start and end of those messages. That's what framing is all about. In this segment, we'll look at different methods which can be used for framing. First of all, we'll look at a byte count method. This is really a motivational method just to get our hand around some of the different issues. Then we'll look at byte stuffing. Byte stuffing is a method which is used in practice. And finally, we'll look at bit stuffing, just to show you an alternative. That's actually an older method. Now, I do want to point out that that all of these methods impose a framing structure on top of any bit stream. You could use them in systems you design. In many real low layer links, however, the physical layer and the link layer are implemented together, and the physical layer often helps the link layer framing by providing signaling about the boundaries, for instance by using physical layer symbols that can't otherwise occur to indicate the start of frames. So we're not looking at those methods. Okay, so our first method, byte counts. What would you do if you wanted to impose a framing structure on a bit stream? Here's a brilliant idea. We'll just start the beginning of each frame with a length field. That length field will tell us how long the frame is. That way we'll know where it ends and where the next frame begins. It's a simple method, it's fairly efficient, and hopefully it's good enough. What could possibly go wrong? Well, here we can see an example of byte counts. I'll just show you here. The first byte here is 5, so that says this frame is 5 bytes long. 1, 2, 3, 4, 5. So if we hop beyond that, we'll get to the start of the next frame, and so on. You can see, oops, almost missed that. We're hopping down, and we'll hop past. Great, there's our simple scheme. There is a problem with this scheme though, as you might guess, and the problem is this. If we ever lose synchronization because of an error or for whatever reason, aside crashing and restarting, then it is very difficult for us to find the start of frames once again. We really have no way to resynchronize and we could be lost forever. Here's an example. First of all, we've got a nice byte where we're in sync. It says 5, we go to here. This byte is an error. It should have been a 5 or something. If we interpret it now as a 7, we're going to overshoot and interpret something else as the beginning of another frame. After that, we will happily invent fictitious frames. Here, 1 byte, okay, the next one must be here, 2 bytes, the next one must be here, 4 bytes, 1, 2, 3, 4, we must be, here. 7 bytes, we're somewhere else. But we've lost synchronization, we can no longer work out when frames start and end. Byte stuffing is a better idea that allows us to resynchronize. The idea with byte stuffing is that we will use a special character called the flag byte to indicate the start and end of frames. Here it is here. We put down a special character that we can look for to know where frames start and end. Of course, to do this, we're going to have to do something with flag bytes which might occur in the middle of a payload as real data. We'll have to escape or stuff these flag bytes with an escape character it's like quoting material to indicate that it's not really the real flag. There's a small complication here too. If we introduce a special character like an escape code, we'll also have to escape the escape code because there might be escapes in the real data. Here's an example of byte stuffing. The rules here are every time you see a flag in the data, replace it with the sequence escape flag, an escape flag. And every time you see escape, replace it with escape. That's it. So we can fill out this example together. On the other side, you'll have A, then there's a flag. We better escape that. ESC flag B. Similarly, if we have an escape inside the data, ESC, ESC B. You could have a escape flag, but if that's actually the data and we want to stuff it, you will have to escape the escape. Then you will see a flag character as a literal and you will escape the flag. And similarly, let me escape the 2 escapes. And the receiver is going to apply the same rules in the other direction. Whenever it sees an escape in the data, it's going to take it out and replace it with the following character. If we use this scheme, it has the virtue that any unescaped flag is now the start or end of a frame. So we can use this method to quickly resynchronize if there's ever any error to find the start of frames. All we have to do is look for that unescaped flag, which doesn't exist here. You can see all of the flags are actually escaped, so they're not real. Okay, there's also another kind of stuffing. You can do stuffing at the bit level. Here's how that would work. So we will call our flag sequence 6 consecutive ones. The rule we'll use at the transmitter is if you ever send 5 ones in the data, send a 0 just in case the 6th thing was going to be a 1. On receive, you're going to do the opposite. If you ever get a 0 after getting 5 ones, throw it away because it was added by the sender. This is quite a simple scheme. Actually, this scheme came before byte stuffing. If you do an analysis, you would expect that this scheme actually has slightly less overhead. Nonetheless, it's more complicated than byte stuffing because we might have to deal with messages with, for instance, 193 bits. And we would rather deal with whole octet or byte numbers. So byte stuffing is what's used in practice. Oh, we have an example here we can go through. So let's just quickly do a little bit of bit stuffing. 0, here's the data, I'm going to copy it down. 1, 1, that's 2 ones in a row, then a 0, oh, no problem. Here we've got 1, 2, 3, 4 ones in a row, now 5 ones, problem. You have to insert a 0. Now we continue. The next one I'll count as 1, 1, 2, 1, 3 ones, 4 ones, 5 ones, 0. Now we're up to here, 2 ones, 3, 4, 5 ones, 0. Then 1, 1, 0, 0, 1, 0. No problem. Here are the characters I've inserted by stuffing. This slide just cleans it up a little bit. And I've already told you how it compares in terms of maybe being slightly more efficient, but being more complicated and not worth it in practice. Now that we've seen how framing works, I can give you an example of a real protocol. PPP is what the protocol is called. It stands for the point-to-point protocol. It's fairly widely used in the internet to carry IP packets to frame them over any kind of bit stream, byte stream transport. For instance, PPP is used to carry IP packets over SONET optical links. You might not know what SONET optical links are, don't worry too much. These turn out to be the big fat pipes that run at many gigabits a second, which are used by ISPs in the middle of the backbone. Here's a little more on how PPP works. First we have the protocol stack here. You can see the IP layer here is going to produce packets and hand it down to the PPP layer, which is acting as the link layer and providing framing. The link layer is then going to run over the SONET layer, that's the physical layer here. And once we've got a little bit of a physical layer, eventually it'll go out that optical fiber. On the right hand side it shows us some of the encapsulation and just some of the real world wrinkles that you run into here. The IP packet is encapsulated inside a PPP frame, that's pretty much what we expect. But the PPP frame might actually be split across 2 SONET payloads. It's a sort of real world complication that networking protocols are full of. If we focus on the PPP bit, since that's our focus for this video, then we find that PPP frames the packets it gets from the IP layer using byte stuffing that in a way that's quite similar to what we've described. Here's a picture of the frame. The payload is what comes down from the IP layer, and you can see to that the PPP layer adds some of its headers and control information and also some trailers. And then the outer layer is the framing with our flags. In fact, the flag character here is 0x7e, and we'll also have to escape this character if it occurs inside the IP packet that's inside the payload, and we'll do that using 0x7d as the escape character. There's one slight twist here though that's a little interesting. It's in the details, but I think it's interesting, so I'm going to tell you. Here's the rule for byte stuffing. To stuff or unstuff a byte, you add or remove the escape character, just as we've seen, and you also XOR the byte which follows the escape character with 0x20. Now if you expand all of those bits and look at that hexadecimal notation, you'll find what that does is toggle the 5th bit So for instance, if I have 0x7e in the data, so 7e, if I stop that, I will get 0x7d, the escape character, and then I'm going to XOR 7e with 0x20. That will flip the fifth bit, and I'll actually get 5e. I've just changed the value of one bit. Similarly, if you stuff 0x7d, then what you'll get is 0x7d, the escape character, and then I XOR 0x7d with 0x20, and I will get 5d. And at the receiver, I'll do the reverse. I'll simply XOR whatever comes after the escape character with 0x20, and that will turn it back into the 7e that we wanted. The virtue of using this scheme is that we've completely removed occurrences of the flag character 0x7e from the contents of the frame. So now we can just search the byte stream for 0x7e, and when you see it, you've got the starter frame. It can't occur inside the frame because we've modified it in some way by using this convention. Okay, well now you know about real link layers and how framing is done.